Alright guys, so let's get started with today's video where we are going to finish up our section 5.2 that we started last week. So section 5.2 we said was going to be the resultants of a distributed load. Basically what we were wanting to do is if we had a beam, maybe simply supported, and it had, I don't know, some functional load on it, right? Some functional load. Just call it W of X. And it's got some length, right? The length of W, which is the length of the load. What we're really trying to do here is to come up with a single resultant force that we labeled FR. Some single resultant force that will have the same effects on this beam as the functional load W of X. All right, so that's what we're trying to do, is be able to take a distributed load and come up with a single resultant force that acts and does the same thing as the functional load. All right, so last week we kind of talked about this, and we basically said that the area under the curve, the area under the load curve, this area here that I've hatched out in blue now, would be the magnitude of our resultant load FRs, right? And so we all know how to find the area underneath the curve. That's obviously the integral. So in mathematical terms, basically what we said was that the magnitude of the resultant load was the integral of W of X, but only from 0 to LW, which was the length of the uniform load. So if we just do that, and we integrate that function over that length, we'll get the magnitude of the resultant force. All right. So that's what we covered in class last week. This time we need to talk about where on this beam will this resultant load act that can replace the distributed load. And basically what we're going to figure out here is that we need to sum moments about a point such that the moment of the distributed load equals the moment of the resultant force about any point. So basically what we do, we're just going to isolate the load, okay? I'm going to redraw it just so it's a little bit bigger and we'll be able to look at this a little better. Okay, so we've got some load that's a function of X. We'll call it W of X. It's got some length, LW, and we're trying to figure out a force, FR, that maybe acts at a distance X bar. And we want these moments to be the same. So what we're going to do is let's take moments about a different point. We'll call this point O, okay? All we got to do is take moments of the functional load about the point and then make those equal together. All right, so let's start off with the resultant force, okay? The resultant force is pretty easy. What is the moment of the resultant force about point O? If we sum moments about point O, what we have then is we have the resultant force FR times X bar, right? That is the perpendicular distance between point O and FR is just X bar, right? So FR times X bar gives us the moment about O. So that's the moment from the concentrated load, but what is the moment of the integral load? Don't quite know that. So basically what we need to do then is integrate this curve, all right? And we're going to look at this as if we have a strip here. This thin strip is going to have width dx, right? And that dx strip is going to be some x distance away from point O. So if we were to break this up into an infinite number of strips that have infinitely small width dx, the height of all these strips is going to be w of x. The width of this strip is dx. So if I take a width and a height of a strip underneath the load curve, that's actually going to give me a force, right? So the force then times this light blue x dimension down here, this one, that will give me the moment, but I've got to integrate that from point O all the way to LW, all right? So basically what this comes out to be then is the moment about point O of the distributed load is W of x times dx to get the force amount, and then multiply that by x to get the moment. So putting this in math over here, it's x w of x dx, and then for us to know what the entire moment is across the entire distributed load, we integrate from 0 to LW. So it's pretty much the same thing as the magnitude, but instead of just integrating the W function, we've got to multiply x into the W function and then integrate. So if we rearrange this, then if we're trying to find x bar, right, this x bar is what is the end game. That's what we're trying to find. If we just rearrange our equation, then we find that x bar is just 1 over FR times the integral of x w of x dx. Okay, so we can use this equation then to figure out where the where the location of the resultant force will act. So now that we know that if we have a load, we can integrate it to figure out the magnitude of the resultant force, and then if we just multiply by x into our functional load and integrate again, then we can find our location of the resultant force. All right, so let's do a couple of examples on this just to prove what we're learning here. So this first example, we've got a uniformly distributed load, right? So that's a rectangular load. It's not a triangle, it's not a trapezoid, it's a rectangular load that has a length of W and a magnitude, or I'm sorry, a length of L and a magnitude of W. So let's just draw this just so we know what we're looking at. We've got some uniform load. It's just a rectangle, right? And we got, it's got the force arrows, it acts down. What we're trying to do is come up with a resultant force that acts at x bar. You can choose any point to do this. About the best point to do it, though, is just the left side, the left point of the load. And so we've got this uniform load of W. It's got length L, and we're trying to find out the magnitude and location of the resultant force. So magnitude of the resultant force, we just integrate the load. So what is W of x? If I start x, the easiest thing to do is always just start x on one side or the other. I'm just going to choose x to start at the left and go right. So if this is an xy coordinate system, all right, let's just redraw this as here's x and there's y. So if this is an xy coordinate system, and this top line, this W, this blue line that I just drew, if that is the line of our function, what then is W of x? All right, this line has no slope to it, right? It's completely horizontal. It has no slope. So the W of x for this particular function is just W. All right. So no matter what the X is, the load is still just W. So if we take this and we integrate our W of X to get the magnitude of the load, what we can say is the magnitude of FR equal to 0 LW, which is in this case is just L, right? The length of the load is just L. So 0 to L of W of X. This time it's just W, right? W of X is just W. And then we just say dx. So what we get here, if you integrate this, we just get W times the integral of X evaluated from 0 to L. And if you perform that integration, what we find is that the magnitude is just equal to WL over 2. Correct? I'm sorry. It's just WL. My mind is not working this morning. Okay. So now that we have that, we need to find what X bar is as well. So X bar, we said, was 1 over FR times the integral of 0 to LW, in this case it's just L, of X times W of X dx. So if we end up doing this math, we get 1 over WL integral 0 to L of X times W of X, which is just WX, right, times dx, and what we get is 1 over WL integral of WX squared over 2 evaluated from 0 to L. And what we find then is that X bar is just equal to L over 2. All right. So for a uniformly distributed load, basically we found that the magnitude of the load, we found this mathematically through integration, the magnitude of our force resultant is just equal to W times L, right? And that makes sense because it's just a rectangular load, and the rectangle has length of W and a height, the rectangle has a length of L and height of W, so the area of that rectangle is just WL. So that makes sense. And also, since it's a rectangle, the resultant force, it makes sense, right, that the force is just acting in the middle, right? It's completely uniform. So you would imagine then that the resultant force would act in the center, and mathematically it does. We found out that the force resultant acts at L over 2 from this point that we started X at, this point over here in the bottom left of the load, right? So that's what we find. And what we find is that no matter what W and L are, this equation holds true, right? So for every rectangular load that there is, for every uniformly distributed load, the magnitude of the resultant is going to be WL, and the location is going to be at L over 2 from wherever the load starts at. Okay, this is every time. All right, so let's do the same thing then, but for a triangular load, okay? Let's just keep continuing on with our example. Let's say we've got a triangular load. And the magnitude of the triangular load up here at the top corner is W, right? And the magnitude of the load at the bottom left corner is 0, right? There is no magnitude of the load over here at the bottom left corner, right? What we're trying to do, again, is find some force resultant, but let's just think, is our force resultant going to act somewhere here? Is it going to act in the middle? or is it going to act somewhere off to the right? Let's just think about it. And if you can think about this, the answer is it's going to act to a little bit to the right, correct? Like we've talked about this in class a little bit last week, where that resultant force, for it to be in the same location, to have the same effects as the distributed load, the resultant force is going to be skewed off to one side, right? So we've got this resultant force. This will be Fr. It's going to act at X bar away from the left edge, right? And then we have this uniform length, or the length of the distributed load, sorry. It has length of L. Okay, so what we're trying to figure out is what is the magnitude of Fr, what is the distance X bar from this point that's on the left side. We'll just label it 0.0 just for labeling purposes, all right? So let's start then. All we've got to do is take our moments about 0.0 to figure out all of this, but we need to know first off what the magnitude of Fr is. And in order to do that, let me erase this, we need to know W of X. All right, and for us to know W of X, we got to set up our coordinate system again, right? So our coordinate system, the x-axis is going to be in the length of the load, and then our y-axis will be starting at 0.0 going up. And so if we set that as our coordinate system, what is W of X? What is the value of W for any distance x if x starts on the left side and goes to the right? Okay. This line obviously has a slope. And what is the slope of this line? Well, the slope, it rises W and it runs L. So the slope is W over L. So, and we know that our equation of a line is mx plus b, right? So m is W over L. We multiply that by x, and then we need to add in our y-intercept. But for this particular line, our y-intercept is just 0, correct? So if this is our equation for W of X, let's go ahead and just mentally check it. What if I plugged in 0 for X? What is W of X? It comes out to be 0, and that's what our line shows. And if I plug in L for X and plug that in into W of X just consolidates down into W, which is what our line should be. So we know that this line, this equation for our line is now correct. So now that we've got a accurate equation for our functional load, let's integrate to find out the magnitude of our functional load. Integral from 0 to L, right? We're only worried about the length of the load itself, which is L, of W over L times X dx, which comes out, you can pull out the W over L, you can integrate X, that becomes x squared over 2, and we evaluate that integral from 0 to L. And what we find then is that the magnitude of this comes out to be WL over 2. Now let's just stop and think about this. We've got a triangle that has a height of W and a length of L. What is the area of a triangle? If you recall from your geometry, it's just 1/2 b times h, right? So the area of this particular triangle would just be 1/2 of W times L, which is what it is, and we have proven it mathematically, all right? So the magnitude of our triangular load is WL over 2. And that is always, right? That is, does not matter what the values are for W and L. Every triangular load will have a magnitude of WL over 2. All right. Next step is to figure out where this force resultant acts so that it has the same effects as W. So we know that our equation for X bar is 1 over FR times 0, integral from 0 to L, times x, w of x, dx. So if I start plugging in all my variables, what we can find then is that w over L times 2 w of L, that's not squared, right? Let's rewrite that so it doesn't look like I'm saying squared. 2 times w over L divided by WL over 2, that's the 1 over FR, and also pulling out the W over L. That'll give us the integral from 0 to L x squared dx. So W's cancel, and what we end up with is just 2 over L squared times x cubed over 3 evaluated from 0 to L. And what we find then is that x bar is just equal to 2/3 L. Okay. So for a particular triangle, any triangle, the resultant force is going to act 2/3 L from the small end. All right, it's not going to act in the middle. It's not going to act at L over 2, right? It's going to be skewed over to the side of the triangle that is bigger, correct? And that distance is 2/3 L, and that is for every triangle. For every triangle of the centroid, or the resultant is going to act at 2/3 L from the small end. And vice versa, right? We can also say that it acts at 1/3 L from the big end, correct? So these are our equations for a uniformly distributed load, which is a rectangular load, and for a linearly distributed load that starts at 0, right? That's a triangle load. All of these equations right here hold true for every load. Okay? Let's take one more step and turn that linear load, then let's turn it into a trapezoidal load that instead of starting at 0, maybe the load has an initial value, right? So we've got this load. We'll say this left side has a W1 and a W2, right? So W1 is not 0 anymore. Our trapezoid load has some initial load, and it goes up to W2. And we're still wanting to figure out the resultant force. And just like the triangular load, it's going to be skewed to the bigger side, right? It's going to be skewed closer to W2. So this is FR. This distance we can say is X bar. The entire length of the load we'll just say is L. And we're going to start X over here at the left, right? So first things first though, we need to figure out what our function is for our line. And just for clarity's sakes, I'm going to label this point here as point O. It's kind of the origin of this system. We're going to label X that goes in the length of the load, and then Y acts perpendicular to that. So what we're looking for is W of X. And W of X for this particular function, how much does our load rise, and divided by how much does our load run, right? So the rise of this function, W2 minus W1. The run of the function is L. We've got to multiply that by X because it's a line, right? Mx plus B. And this time, instead of our y-intercept just equaling 0 like it did for the triangular load, we do have a y-intercept of W1. So that is our function for our load. That's the functional load. If we integrate this to figure out what the magnitude of our resultant load is, we integrate from 0 to L, and we just perform the integration. I trust that you guys know how to perform the integration of this, but what we basically find is, I'm just going to write the answer here. The magnitude of this functional load comes out to L times W1 plus W2 over 2. And for any of you geometry savvy guys out there, you know that this right here is just the equation for the area of a trapezoid. And the way I like to look at this is it's just the average height, right? It's just the average height of this trapezoid. And then, the average height of the trapezoid times the length of the trapezoid, right? So W1 plus W2 over 2 gives you the average height of the trapezoid. Multiply it by L, that gives you that area, basically, of this rectangle. All right, so that makes sense. We know that the area of the trapezoid is the average height times the length, which means that's the magnitude of our resultant load. If you guys want to run that math out and to test it for yourself, feel free to. But now what we need to do is we need to figure out the location of x bar with respect to this point O. And all we've got to do for that, again, is integrate. Is 1 over FR times the integral 0 to L of x times W of x dx. So if we put that in, then we get, we can say it's 2 over L times W1 plus W2, right? That's the 1 over FR. We integrate from 0 to L of W2 minus W1 over L x squared plus W1 x dx, right? Everybody agree that this first term outside of the integral is just 1 over FR, and then the integral is x w of x, so all I did was multiply w of x. We just added an x term into each one of those components, and then we integrate from 0 to L. So performing this integration, what we find is that x bar comes out to be L over 3 times W1 plus 2 W2 all over W1 plus W2. Okay? So that's what x bar comes out to be. And that is the location of the resultant force. I want to make a note though here that we could have done this a different way, all right? We could have, instead of treating this load as a trapezoid, we could have treated this as two separate loads, right? We could have treated it as a rectangular load that has a magnitude of W1, and then a triangular load, a rectangular load with magnitude W1, and then a triangular load that has magnitude of W2 minus W1, and just worked those two together. Since we already know how to work with a rectangular and a triangular load, we could have broken this trapezoid down into a rectangular and a triangular load. So that's what we're going to do right here. We're going to redraw this real quick. We're going to redraw our trapezoidal load, but this time we're going to break it up into a rectangle and a triangle. And we can sum moments about that point O to figure out what we've got, right? So we know FR is going to act somewhere over here, and it's going to have an X bar dimension. And if we just sum moments about point O, this is what we get. Sum moments about point O, we know that FR times X bar, that's the moment of the resultant force, right? Now that's got to equal the moment of the applied forces, which is the distributed loads. What is the moment of the, let's just start with the distributed load, right? The distributed load is going to act right here in the middle of the rectangle. So the moment then is W1 times L. That's the magnitude of that force, and then we multiply it by L over 2 because that's the centroid of the rectangle, right? Then we can do the same thing for the triangular load, where the resultant force of the triangle acts over here, and we just take its moment as well, and we know that the magnitude of the triangle force is 1/2 B times H. Well, 1/2 B is L, right? And H becomes W2 minus W1. So that's the magnitude of the triangle force. And then all we have to do now is multiply it by a moment arm, whatever the distance is from that force to point O. And we know that distance is 2/3 L. And we know that this FR is the area of the trapezoid. So rewriting all of this, we know that X bar is equal to 1 over FR, which is L times W1 plus W2 over 2. And then you just multiply all of this together, which is W1 L squared over 2 plus L squared over 3 times W2 minus W1. And if you were to perform the math out on this and condense all this down, what you find is that X bar will also still equal L over 3 times W1 plus 2 W2 all over W1 plus W2. All right. That's what you find. Okay. So there's two different ways there to solve for the same thing. You will find, though, in practice, when you're actually working with problems here in the next week or so, when we're looking at finding reactions for beams or anything, right? The easiest way to do this is probably to break this trapezoidal load into a rectangle load and a triangular load. So this method that we did down here in the bottom, where we broke it up into two different types of loads, that will probably be the most efficient and most effective method for dealing with trapezoidal loads. All right. All of this will make more sense once we start putting in some applications on all of this stuff here. It'll make more sense later. But first off, we just need to know how to work with these loads. So let's move on to our last example then, and actually work with a functional load that's not linear, that we couldn't, something that we actually couldn't if we wanted to just break into basic shapes, okay? So let's say that we've got a load, W of x, right? And the particular load starts here, and it looks something like this, right? And it acts downwards. Remember, all these loads could also act upwards if we wanted to. This here is W of x, and W of x has been given to us up here in the problem statement. It's negative 2x squared plus 4x plus 16. All right, so we already know what W of x is. Let's draw our coordinate system. We'll start x here. We'll start y over here. This point will be the origin. What we're trying to do is find the location of the force resultant. Now, it may be tempting to say that this force resultant acts at the maximum load of W, right? At the maximum point of W where the curve tops out. It may be tempting to say that, but that's not particularly true, all right? So we're just going to draw it off to one side or the other, just so we're not confusing ourselves. So we'll say that we've got FR. FR acts at X bar, and our load has length of L. And again, we'll start X at the left and go towards the right. Okay? So again, this is the same thing. It's just now the function is not going to be linear. So we know that W of x is given to us. Negative 2x squared plus 4x plus 16. We know the magnitude of the load is just equal to the integral over the length of W of x. So that is going to come out to be magnitude of the resultant is just equal to negative 2/3 x cubed plus 2x squared plus 16x evaluated from 0 to L, right? If you do that, what we find and keep in mind, right, that all of these values, I'm sorry guys, the problem statement, I didn't draw it on here. The problem statement said that the length of the load is 4 feet, right? So now when you evaluate your integral over here, instead of it just being 0 to L, we integrate from 0 to 4, correct? So just evaluating that integral right there, the negative 2/3 x cubed function, just plug it in 4 for x, what we end up getting is that the magnitude of our resultant force is 53.33 pounds. Right? So that's equal to 53.33 pounds. Now we need to figure out the x bar dimension. Now that we know the magnitude of the load, we need to figure out the x bar dimension. So it's all still the same equations, where x bar equals 1 over FR integral 0 to L of x times W of x dx. So that just comes out to be 1 over 53.33, and you just add in an x into your load function. So we'll have negative 2x cubed, and then you integrate that, so we get negative 2/3 x to the 4th plus 4x squared integraled, which is 4/3 x cubed, and then 16x integrated gives us 8x squared, and then you evaluate that integral from 0 to 4. All right, so all I did there was just add in an extra x into each component and then integrate each component. So if you run this math out then, because at this point it's just math, right? We find that x bar is equal to 1.6. And since our units were in pounds per foot when we integrated, because that's what the load function was given to us, our load function W of x was given to us in pounds per foot. That means that our answers, if we integrate all of that, comes out in pounds and feet, and we know that x bar is going to be a distance, so it comes out in feet, right? So that's good. So we found the magnitude and the location of the resultant force. The last little bit of this problem wants to know, though, it says also what is the maximum intensity of this distributed load, right? So I'm trying to figure out what is that maximum intensity on that curve. So all of you people who are good at Calc 1, you will just remember that all we have to do is take the derivative of the load function and set that equal to 0, right? Because that is a maximum of the function. So if we know W of x, this will be part 2 down here. So W of x was negative 2x squared plus 4x plus 16. If we take the derivative of W with respect to x, what we get is negative 4x plus 4, right? So I want this equation right here to equal 0. So when the slope equals 0, that the slope of that is negative 4x plus 4, we find that x equals 1, right? So if we then plug in 1 back into W of x, then that'll give us the location of the maximum load. So W of 1 equals W max. And what that comes out to be is 18 pounds per foot. So at its maximum, at its utmost maximum, this load, the value of this point right here, is 18 pounds per foot. All right. So that is how we work with distributed load. That's how we find their resultants. That's how we find the location of their resultants. For the most part, unless it's a functional load, you will not have to integrate, right? This is all just proving these equations. If we look back up here on this second page where we figured out the magnitude and location for rectangular loads and for triangular loads, this right here is 95% of what you need to know. As long as you can remember the formulas for rectangles and triangles, you can break down 95% of the kind of loads that you'll ever see into these two shapes. Because if we have a trapezoidal load, which is very common, that trapezoidal load can just be broken into a rectangle and a triangle. And then very, very rarely do we have functional loads like this where we actually need to integrate, okay? But if you can remember rectangular loads and triangular loads and how to work with their resultants, you will have 95% of what you need to know memorized, all right? So that's it for today. Section 5.3 or section 6.1. I think we're going to go ahead and start working with section 6.1 next. Where we're actually going to start talking about 2D equilibrium of a rigid body, right? So if you'll recall, some of our past lectures have been on 2D and 3D equilibrium of a point. We're going to take that up and step it up a little bit and do 2D and 3D equilibrium of a rigid body. So it's the same thing pretty much as what we've been doing, but just one more little step up added to it, and we'll start working with that, all right? So be looking for that video coming out shortly, and hope you guys have a great day.